Binary search. If there's one algorithm interviewers expect you to speak fluently, it's binary search. It's the litmus test for algorithmic rigor, pointer discipline, off by one control, and logarithmic thinking. This pattern mastery 100 staple shows up everywhere, from search problems to boundaries and monotonic checks. Let's lock it in using basics so your explanation and code are crisp and unbeatable. We're given a sorted array nums and an integer target. Return the index of target if found, otherwise return -1. Because the data is sorted, we can eliminate half the search space each step by comparing the middle element to the target. Binary search runs in O log n time and O1 space, way better than a linear scan. Key pitfalls: computing mid, updating left and right correctly, and using while left less than equals right to avoid infinite loops. We'll return as soon as nums mid equals target, else move the appropriate boundary. Plan: initialize left equals 0, right equals len nums -1. While left less than equals right, compute mid. If nums mid equals target, return mid. If it's smaller, discard the left half by doing left equals mid plus 1, otherwise discard the right half via right equals mid -1. If we exit the loop, return -1.
Let's try to implement it using solution 1. We begin by defining a class named solution. This simply organizes our function inside a neat container. This sets up our function binary search, which takes a sorted list called nums and a value called target that we want to locate inside that list. We initialize 2 pointers. L at the far left, index 0, R at the far right, the last index. These pointers mark the current search boundaries. We continue searching as long as our left pointer has not passed the right pointer. Because we keep having the search area, this loop runs in O of log n time. We compute the middle index between L and R using integer division. The midpoint is where we check next, just like flipping to the middle page of a book to decide whether to look left or right. We check if the value at the middle index matches the target. If it does, we found exactly what we're looking for. And if the middle value is the target, we return the index and end the search. If the middle value is smaller than the target, that means the target must be to the right of mid, so we shift our search window to the right half. To search the right half, we move the left pointer just past the midpoint. This covers the final case. The middle value is greater than the target, which means the target must be in the left half of the list. So we move the right pointer just before the midpoint, shrinking the search window to the left side. If the loop finishes and we still haven't found the target, we return -1 to indicate that the value is not in the list. And that's how this algorithm works. It sets up left and right boundaries, then keeps having the search space by comparing the midpoint value with the target until the value is found or the range collapses. Efficient, simple, and elegant. Check. Let's walk through this test case as if we just ran it through the binary search solution. Input is nums equals -1, 0, 3, 5, 9, 12. Target equals 9. Here, nums is a sorted array. We want to find the index of the value 9. If it exists, return the index. Otherwise, return -1. Why the output is 4. Let's inspect the array. Index 0 gives -1. Index 1 gives 0. Index 2 gives 3. Index 3 gives 5. Index 4 gives 9. Index 5 gives 12. The value 9 clearly sits at index 4. The binary search process also confirms this. It checks the midpoint. It narrows down to the right side when the midpoint is too small. It continues until it hits nums at index 4, which equals 9. So the correct answer is 4. The output 4 matches the expected 4, confirming that the binary search implementation is correctly locating the target in a sorted array. Now let's try another implement approach using solution 2. We start by defining a class named solution. This simply holds the function we're about to build. This sets up our binary search method. It receives a sorted list of numbers called nums, and a target value that we want to locate. Inside the main function, we define a helper function. This helper takes 2 numbers, L, the left boundary, and R, the right boundary. It will perform the actual recursive binary search. This is our base case. If the left boundary crosses the right boundary, it means there is nowhere left to search. In that case, we return -1 to signal that the target does not exist in this part of the array. We calculate the middle index of the current search range. Binary search always checks the midpoint first, like checking the middle page of a book to decide which direction to flip. Here we check whether the midpoint value matches the target. If it does, we return the index immediately. The search is complete. If the midpoint value is smaller than the target, it tells us the target must be somewhere in the right half of the current range. So we recursively call helper, updating the left boundary to just past the midpoint. This halves the search range, giving us the classic O of log n time complexity of binary search. The final case is when the midpoint value is larger than the target, meaning the target lies in the left half of the range. So we call helper again, adjusting the right boundary to just before the midpoint. To start the whole process, we call the helper on the full search range, from index 0 to the last index of the list. And that's how this algorithm works. It sets up a recursive helper that receives the current left and right boundaries, then continually halves the search space by comparing the midpoint with the target, moving left or right until the value is found. Efficient, simple, and elegant. Check. Let's walk through this test case using our binary search logic. Input is nums equals -1, 0, 3, 5, 9, 12. Target equals 2. Here, nums is a sorted array, which is exactly what binary search expects. We're trying to find the index of the value 2. Why the output is -1. Look at the values in the array. -1, 0, 3, 5, 9, 12. The value 2 does not appear anywhere. Binary search will confirm this by checking the midpoint, which is 3, too large, so it searches left. Then checking a smaller midpoint region, which is 0, too small, so it searches right. Eventually the boundaries cross, meaning the value is not present. Since the target never matches any element, the correct return value is -1. The output -1 matches the expected -1, confirming the function correctly reports when a target is not found in a sorted array.
Let's have a quick recap. Breakdown recap. So, to wrap it up, binary search is all about finding a target efficiently in a sorted list. Instead of checking one element at a time, we cut the search space in half with every step, comparing the middle element to the target. Assess recap. We compared approaches and saw why this one stands out. A linear scan takes O(n) time, but binary search drops it to O log n. The key challenges aren't in the math, they're in managing pointers, avoiding infinite loops, and computing the mid correctly. Structure recap. The logic was straightforward. Set 2 pointers at the start and end, find the middle, and adjust the search window based on whether the target is smaller or larger. Keep narrowing until it's found or the window closes. Implement recap. When we implemented it, everything came together through a clean loop that halved the range at each step. The left and right pointers guided the search precisely, and returning the mid when found kept the function minimal and robust. Check recap. We ran multiple test cases, finding numbers correctly and returning -1 when not found. Every run matched expectations, confirming our binary search logic worked perfectly in logarithmic time. The big takeaway? Binary search isn't just a single algorithm, it's a mindset. Mastering it trains you to think in halves, control boundaries precisely, and reason with mathematical efficiency, skills that show true algorithmic discipline in any coding interview.